This is the lesson on image resampling. Resampling is a common basic manipulation often needed to resize an image. Why would we want to do this? Perhaps we want to downsample an image prior to uploading it to a web page so that it is more compact and web display is quicker and more efficient. Or perhaps we have an image display device that has pixels in 1,000 rows by 1,500 columns. But the image we have is not the same resolution as our display. Our cameraman image, for example, is only 256 by 256. If we want this image to be resized to fill out the entire array of 1,000 by 1,500 pixels, what do? Anytime we need to resize an image, we need to resample it. Similarly to how we resampled one-dimensional signals with the interp1 function, we can interpolate 2D signals. For 2D signals, we use the interp2 function. And images, as we said, are essentially 2D signals, so we can resample images using the interp2 function. What we will see is that MATLAB has many image processing and analysis functions. These functions operate on input images to analyze or process them and output a desired result. Let's take a look at the interp2 function. The first argument is the image matrix. The function needs the matrix to be data type double, so we can wrap the variable image with the double function since our image is data type uint8. So our first argument is the R by C double matrix. The next two arguments are the column and row coordinates for the points that we would like to interpolate. So the second argument is our horizontal coordinates, which will take on values between 1 and C. And the third argument is our vertical coordinates, which will take on values between 1 and R. As we saw with signals, there are multiple ways to interpolate, such as linear and spline interpolation, and a fourth argument could be used to control the type of interpolation. When left empty, the default is linear interpolation. Let's look at an example. Consider the 2x2 block of numbers in rows 1 to 2 and columns 2 to 3 of our cameraman image. These pixels have value 159, 158, 154, and 157. When we take that tiny 2x2 block of 4 pixels and display them as an image, we get a result that looks like this. We can use interp2 to linearly interpolate this image matrix. First, let's look at an integer grid point at column coordinate 2 and row coordinate 1. As expected, the function returns the exact value at row 1, column 2 of the matrix, which is 159. Now let's go to a non-integer off-grid point. At row coordinate 1 and column coordinate 2.5, linear interpolation will give us a weighted average of the pixel value at row 1, column 2 and row 1, column 3. This is because this coordinate falls between these two pixels. Since this coordinate is equidistant to these two pixels, the weighted average weights the importance of both pixels equally in the average, so interpolation gives us the arithmetic mean of 158.5. Similarly, if we go to row 2, column 2.5, interp2 returns the average of the pixel at row 2, column 2 and row 2, column 3, because this coordinate falls halfway between these two pixels. So interpolation returns a weighted average with equal weighting on the bottom two pixels. This results in 155.5, as this is the average of 154 and 157. Next, if we go off integer coordinates for both the rows and columns, at column coordinate 2.5 and row coordinate 1.5, we get 157. Why is this? Row coordinate 1.5 and column coordinate 2.5 are equidistant to the centers of all 4 of these pixels. So 2D linear interpolation computes a weighted average of the 4 pixels with equal weights because they are equidistant. This gives us the arithmetic mean of the 4 pixels, which is 157. Finally, we can also go somewhere else between the 4 pixels that is not equidistant to multiple pixels. For example, row coordinate 1.75, column coordinate 2.25. At this location, we are closest to the row 2, column 2 pixel, but not directly on the center of that pixel on the grid. We are 0.25 pixels above it and 0.25 pixels distance just to the right of it. Just like the previous example, linear interpolation will give us a weighted average of the 4 pixels whose centers surround this coordinate. The difference is the weighting assigned to the 4 pixel intensities and the weighted average will be different. The highest weight will be assigned to the row 2, column 2 pixel because it is closest to our coordinate. The lowest weight will be assigned to the row 1, column 3 pixel because it is furthest from our coordinate. The row 1, column 2 and row 2, column 3 pixels will receive equal weighting because they are equidistant to the coordinate. The result of the weighted average is a linearly interpolated grayscale intensity of 155.75. With linear interpolation, any coordinate that we would like that falls within the green box with corners defined by the centers of these 4 pixels will be determined by a weighted average of these 4 pixels, where the weight is determined by the proximity of the coordinate to the center of each pixel. Linear interpolation permits using this discrete image matrix to approximate a continuous grayscale intensity function. That is, we can estimate an intensity at any continuous floating point coordinate in the image plane, even though we really only have intensities at discrete grid coordinates. We do not have to limit ourselves to a single coordinate location at a time when using interp 2. If the second and third arguments are equal-sized vectors, interp 2 will consider the second argument as a vector of column coordinates and the third argument as a vector of corresponding row coordinates for a set of 2D points that we want to interpolate. Here are all the coordinate pairs we just inspected individually, concatenated here into a single call to the interp2 function. This also works for matrices of row and column coordinates. If we pass as input a matrix of column coordinates and an equisized matrix of row coordinates, our output is an image matrix the same size as the 2 input coordinate matrices, filled with the interpolated values of the image sampled at those coordinate locations. This lets us use interp2 to resample an entire image in one pass. We simply need to provide all the column and row coordinates of the image locations we wish to sample as matrices, and we can interpolate the image matrix provided as the first argument using those coordinates to form a new image. Let's consider, for example, our zoomed-in 10 by 10 image of the cameraman's face. If we want to upsample this highly pixelated image region by a factor of 10, we can linearly interpolate grayscale values at steps of 1/10 pixel size from row 70 to 79 and column 125 to 134, as these are the pixel coordinates for this region of the image. To create this grid of coordinates, we can use the mesh grid function. Mesh grid produces for us our matrix of column coordinates in big C and row coordinates in big R that we want to interpolate. The first input to mesh grid is a vector of the row coordinates we would like to sample, which are rows 70 to 79 in steps of 0.1. The second input is the column coordinates, which are 125 in steps of 0.1 to 134. Mesh grid produces matrices corresponding to every combination of column and row coordinates across the two vectors. As both of these vectors contain 91 entries, there are 91 times 91 pairs of unique row and column coordinates, and thus C and R will be 91 by 91 matrices. Inspecting the first 5 rows and columns of R, we see we have a matrix of row coordinates that increase from row 70 in increments of 0.1 pixels as we move down along the rows. Similarly, if we look at the C matrix, we see a matrix of column coordinates starting from 125 on the first column, incrementing by 0.1 when going right across the columns. Taken together, C and R define the coordinates we would like to sample our original image to create our upsampled face image. Next, we simply call interp2 with the image, C, and R as the first three arguments. Using linear interpolation, we can see that we can upsample the very pixelated original image by a factor of 10 and create a much smoother looking non-pixelated representation. Now let's return to MATLAB and try upsampling our image using this approach. First, let's load our cameraman image. Recall that our problem is that our image display is 1000 rows by 1500 columns, and our image is only 256 by 256. So we need to use interp2 to upsample our image. First, we define the number of rows and columns that we want the new image to be. Our new number of rows in R is 1000, and our new number of columns in C is 1500. To use interp2, we need to define all of the coordinates at which we want to interpolate our R by C image grid, which we know is 256 by 256. To create our new nr by nc grid, we will need to interpolate between many grid point coordinate locations on the R by C grid. We again use the meshGrid function to obtain our column coordinates matrix, big C, and our row coordinates matrix, big R. The first input to meshGrid is the vector of column coordinates ranging from 1 to C, where the step size between 1 and C is how we choose how much we want to upsample. If we want to go from C columns to NC columns, we should choose the step size to be C minus 1 divided by NC minus 1. That is, the number of columns of the existing matrix, minus 1, divided by the number of columns of the new matrix, minus 1. Similarly, in the rows argument, we want coordinates from 1 to R with a step size of R minus 1 divided by nr minus 1. This will give a vector that is nr elements long with values uniformly spaced ranging from 1 to R. meshGrid finds every combination of our 1000 row and 1500 column coordinate inputs and outputs them in our big C and big R matrices, which we can see are 1000 by 1500 matrices. Now, upsampling our images is easy. We simply call interp2 with our image, C and R as inputs, and the meshGrid function only works for matrices of data type double, and our image has a uint8 data type, so we typecast it to double. And we can see our output matrix is an image matrix that is indeed 1000 by 1500 in size. When we view it, we can see it appears to be virtually indistinguishable from the original image, just represented on a different matrix and stretched on the horizontal axis, which is indeed the result we expect based on how we have upsampled it. We can also use resampling to anonymize our cameraman image, using the more standard pixelization effect rather than simply replacing it with a gray box. Let's grab the submatrix of the image corresponding to the face. To achieve pixelization, our goal is to replace this 46 by 46 block of pixels with a coarse pixelated version to anonymize the cameraman's face. We can do this by first downsampling this image to a coarse resolution and then upsampling it back to the 46 by 46 resolution. To do this, first we define our coarse downsampled resolution to be NR equals 10 by NC equals 10. Our R and C of our face matrix are both equal to 46. Since we have replaced our NR, NC, R, and C variables, our call to mesh grid is exactly the same. As is our call to interp 2. To downsample our face image. And we can see we have a 10 by 10 downsampled image where through pixelization the identity of the cameraman has been obfuscated. Next we need to put this pixelated version back into the original image. To do this we need to resample this 10 by 10 grid back to the 46 by 46 grid from which it came, so that we can replace that 46 by 46 block of pixels with this image. To do this we use mesh grid again, but this time we need to switch NR and R and switch NC and C in our call to mesh grid. Switching NR and R and NC and C in our call to mesh grid, we now get 46 evenly spaced coordinates ranging from 1 to 10 for both the rows and the columns in our big C and big R matrices, which will let us upsample the 10 by 10 image to a 46 by 46 resolution. Running this interpolation on our downface image, and inspecting the result, we see that the upsampled image does not look the same as the pixelated 10 by 10 image. Rather, it appears to be a much smoother version of it. That's because we're using linear interpolation. So each of the densely sampled pixels is determined by weighted average of the neighboring sparse pixels in the 10 by 10 grid, resulting in a continuous grayscale function. If we want to maintain the pixelated appearance, we need to use a different type of interpolation than linear interpolation. If we use what is called nearest neighbor interpolation, then the intensity assigned to each interpolated coordinate is the intensity of the closest pixel, rather than a weighted average of all 4 pixels that the coordinate falls between. We do this with the interp2 function by setting the fourth argument to the string nearest rather than linear. When we run this, we see we still get a grid of 46 by 46 pixels, but with nearest neighbor sampling, the result looks identical to the pixelization of the 10 by 10 grid in our 46 by 46 pixel image. We still see the set of 10 by 10 blocks of constant intensity. Finally, we can replace the 46 by 46 face pixel region in the image with this new anonymized face image. The result is the much more traditional pixelization method for anonymizing a face in an image.